So let's tackle the model that classifies the chest X-ray images using PyTorch Lightning and pre-trained ResNet model. So we are in the medical field using the AI that classifies the pneumonia. So like we have the pneumonia diagnostic assistant that we could have the second opinion if we have if we are the one who look into the results of the X-ray. So it could be our pneumonia diagnostic assistant. So the workflow here is in this deep learning pipeline is we load and inspect medical image data, apply pre-processing and augmentation, create data sets and data loaders. We build a Lightning data module, load pre-trained CNN model, and create Lightning module, configure optimizer plus a scheduler. We train with Lightning trainer. We evaluate predictions and metrics. So the goal of this project is the model predicts chest X-ray conditions such as normal, pneumonia, other lung conditions, and depending on the datasets. So this is an image classification problem. The model learns patterns from X-ray images and predicts the correct class. So the data preparation. So we starts by loading the image folders like we set the variable data/dir, and usually the data structures looks like from the chest X-ray folder. We have the two components, train and validation. In each of those train and validation folder, we have the normal and pneumonia, like that. So we visualize the sample images to understand the data set. So this step is important because in deep learning, we must inspect our data first. Medical datasets may contain imbalance or noise, and image size and quality matter. So next is image transformations. This one of the most important sections. So it defines the train transform and validation transform. So we use the transforms that compose, like we have the transform precise, set to 224 by 224, random horizontal flip, transform random rotation, color jitter, random affine, to tensor, and normalize. What each transform does, so let's say resize. We resize makes all images the same size. Why? Because the convolutional neural network requires consistent tensor dimensions, like 224 is standard for ResNet. Next is a random horizontal flip. So it randomly flips images horizontally. The purpose is to increase datasets variety, help generalization, and reduce overfitting. This is called data augmentation. Next is random rotation. So rotates images randomly, like positive or negative 10 degrees. The purpose is the real X-rays are not always perfectly aligned. The model becomes more robust. Next is color jitter. Like we said, it's the brightness at 0.2 and contrast 0.2. It changes the brightness and contrast slightly. So the purpose is makes the model robust to different lighting exposure conditions. Like in the real world images, it has a different lighting exposure conditions. Next is random affine. This performs translation. It moves image slightly. Example, left, right, up, down. Like 0.1 means up to 10% movement. Next is scale. It zooms images in and out randomly, like 0.9 zoom out, 0.1 zoom in. The purpose is the model learns size invariant features. Next is tensor or to tensor. Convert image into PyTorch tensor data structure. Image shape changes from age or height width channel to channel height width. Next is normalize. We transforms the normalize inside of it. Its argument is mean and standard deviation. So standardized pixel values. This improves training stability, convergence speed, numerical performance. Next is dataset creation. So the function of this datasets is this image folder. It's automatically reads folders, assign labels, and load images. Example, train dataset is equal to dataset.image folder, very common in computer vision. So it reads folders, assign labels, loads images automatically. Next is data loader. It creates data loader construction. But, yeah. Why data loader exists? Training all images at once is impossible. Instead, images are divided into batches. Batches are loaded efficiently. Next is training loader. Reshuffle is equivalent to true. Important. Why? If data order never changes, model may memorize sequence. Worse, generalization. Validation loader. So reshuffle false. Validation must remain consistent during the testing and validation. We don't need to shuffle it because the training is finished. Next is lightning data module. Let's say we have the class chest X-ray data module, and inside the argument is pl.lightning data module. So this inherit those class. This organize all data logic into one class. Why lightning module is useful? Instead of manually handling datasets, data loaders, transforms, setup logic, lightning centralizes them, cleaner and scalable. Next is constructor init. So self.data dir, self.batch size, and transforms. Next is set up a function or method. This is very important. So if you have the code dm.setup, it automatically prepares the datasets. So inside self-train dataset, self.validation dataset is equivalent to create datasets. So when Lightning starts training, dataset already exists. Preprocessing already configured. Train data loader, return training data loader, and validation loader returns validation data loader. Next is transfer learning with ResNet 18. So load the ResNet 18. It uses the pre-trained CNN. What is transfer learning? Instead of training from scratch, we use a model already trained on millions of images. We use learned visual features. Huge advantages is for faster training, less data needed, better performance, especially useful in medical imaging. So ResNet 18 is introduce residual connections. This help very deep network train effectively. Next is replacing the final layer. So if you have the nn.linear and its arguments, the first and second argument is the number of inputs and the number of output. So the original ResNet classifier is replaced because image classes is not equivalent to medical classes. So we create a new classifier head. Next is freezing parameters. Like we disable the gradients or the parameters of those. So we set it false. And if we unfreeze it, we use the param that requires grad equivalent to true. Only train classifier head. This is called feature extraction. The CNN acts as a feature extractor. Next is optimizer and scheduler. So, like we use the define optimizer and scheduler method. So we use the Adam W optimizer. We use the code optim.adamw. Model optimizer we commonly used in deep learning. So the advantages is adaptive learning rate, meaning it automatically adapt the steps in the optimizer. Next is stable convergence and includes weight decay. So weight decay acts like regularization, help reduce overfitting. It regularizes the large parameter. Next is learning rate scheduler. Reduce LR on plateau. This reduces learning rate when validation loss stops improving. Example, loss stops improving, learning rate reduced, and final optimization. Next is lightning module. So let's say we have the class X-ray classifier, and inside of the argument is pl.lightning module. This contains all model training logic. Next is save hyperparameter. So lighting automatically stores constructor arguments, so you can access them later, like using the self.hyperparams followed by the arguments in the constructor. So very useful for logging, checkpointing, reproducibility. Next is loss function. We use the cross entropy loss. This is standard classification loss for images, so we use for multi-class prediction. Next is accuracy metric, and we set the argument task equivalent to multitask, so tracks prediction accuracy. Next is forward. It defines forward pass. So let's say we input the X and the output will be the logits. Training steps. This is where training happens. Typically flow, like we have the batch and we have the image and the labels, and we pass the value of the images in the forward pass and produce the logits, and those logits and the labels compared to the label value would have the loss. So what are logits? Raw model output before softmax. So softmax converts the logits, diba? So example, 2.1 in the vector 0.4, 5.7. So the highest value is predicted class. So why self x works? Because forward is automatically called internally. So self x, self inside of argument is x, means self that forward argument x. So early stopping. So the purpose of early stopping stops training automatically when improvement stalls. It prevents overfitting, saves compute time, avoids unnecessary epoch. Next is validation accuracy. Monitoring validation accuracy. So the monitor validation accuracy mode equivalent to max. Higher validation accuracy is better. So the patience is we divide the number of or average number of epochs into two. I mean divide half. We have it. So training waits several epochs before stopping. Next is trainer. We want the trainer. This lighting training engine. So what trainer automates? Without lighting, you'd manually write each epoch loops, device management, validation loops, mixed precision, callbacks, logging. Lightning handles all automatically. Next is mixed precision. So we set the precision equivalent to 16 mix. We uses the FP16 or precision 16 and precision 32 together. So the benefits is faster training, lower virtual RAM usage, GPU optimization. Next is accelerator. Is we set it to auto. Automatically chooses GPU if available, otherwise is CPU otherwise. Trainer that fit. We use this is not just the enter training process. Lighting automatically calls setup. Loads data loaders, performs forward pass, compute loss, backpropagation, validation, metric logging. Next, evaluation. After training, we conduct the confusion metrics, classic accuracy, random predictions, and displayed. It shows the correct predictions, wrong predictions, which classes are confused. Very important in medical AI. So here's the more important key concept here. So data augmentation, improved generalization, data loader is efficient batching, transfer learning is freeze pre-trained CNN, and feature extraction is freeze backbone, cross-entropy loss is classification loss, and ADAM-W is optimizer. LR scheduler is adaptive learning rate, early stopping is prevent overfitting, mixed precision is faster training, lightning module is organized training, data module is organized data pipeline. So this project demonstrates a strong medical AI workflow, but in real hospitals, remember, models require extensive validation, multiple doctors verify outputs, dataset must be very large, false negatives are dangerous. AI acts as assistants that solve diagnosis. So the systems are usually decision support tools, second opinion systems, and triage assistant.